Now, the next thing we're going to talk about is something called the rank of a matrix. Okay, so a matrix not only has a kernel, which is the set of vectors that it will transform into the zero vector, it also has something called rank. And the rank basically is simply this. It's the number of linearly independent columns that a matrix has. And this turns out to be super important, right? So let's take an example here. Here's a matrix. Let's do the one where it's 0.707, negative 0.707, 0.707, 0.707. Now, we have two columns here. One is the vector 0.707 twice. The other one is the vector negative 0.707, 0.707. And I ask you, are these linearly independent or not? And it's sometimes hard to tell these things at a glance. But the way I think of it in 2 dimensions is I just make sure they're not on top of each other, right? So if I say 0.707, 0.707, well, that's going over 0.707 and up 0.707. So that's that point right there. That's that vector. My second column is negative 0.707 and up 0.707. So it's that column right there, or that vector right there, right? If this is 1 and this is 1 and this is negative 1 and this is negative 1. So clearly these are not right on top of each other, right? And so these are linearly independent, and therefore the rank of this matrix, if we call this A, the rank of this matrix is 2. This is also known as being of full rank. And that means it's as big a rank as it can have. I mean, it's only a little 2 by 2 matrix. It can't possibly have rank bigger than 2, right? Because it only has 2 columns, period. So it obviously can't have more than 2 linearly independent columns. And therefore we call this a full rank. Okay, that is very different than this matrix, which we had a moment ago. I think we call it C, but we'll change it and call it B now, just because that's the next letter I thought of. This guy right here, right? As we mentioned, this is blue dominoes, and therefore there is only one linearly independent column. These two things are really the same column in disguise. There's only one linearly independent one, and again, if we graph them in 2-dimensional space, which is possible to do since we only are doing 2 dimensions here, get much higher and you can't graph it anymore. But we'll see that 1, 3, that column right there is this vector. Ugly. And we see that this column is 2, 6. 2, 6, that is that vector. They are right on top of each other, 1, 3, and 2, 6 are, and therefore the rank of B is only 1. This is a rank-deficient matrix, is sometimes called, which means this doesn't have as many linearly independent columns as it could. It basically doesn't have its act together. It's screwed up in some way. That's how I give a value judgment to this thing. It's sort of rank-deficient. Now, one interesting thing you might realize is that if you look at the rows of this thing, it's also true that they are not linearly independent, right? 1, 2, and 3, 6 are not linearly independent. As a matter of fact, if we plotted those rows, which we don't usually do, but we'll do it now just for illustration purposes, if we plotted 1, 2, and we plotted 3, 6, we'll see that also those are right on top of each other. And it turns out that's always the case. In fact, the number of linearly independent rows is called the row rank of a matrix, and the number of linearly independent columns is called the column rank of a matrix. But you know what? People never use those terms, row rank and column rank, because these are always the same. And so they just talk about the rank of a matrix, and that's all we're going to have to talk about, is the rank of a matrix, okay? Now, keep in mind that for 2 dimensions, it's a little bit easier to see than for 3 or higher, right? So let's do a example of a 3-dimensional matrix, okay? I'm going to give a matrix here, and I'm going to say it's got, 1, 9, 2, negative 4, 4, 2, 5, 13, 2, okay? Now, let's say call this C. What is the rank of C? And that is basically asking how many of these triominoes are linearly independent. Are any of these multiples of the other 2? If so, get rid of it, and we're going to be rank deficient. And again, it's very, very hard to look at this and eyeball it and tell that there is some linear dependence here, but there is. In fact, I concocted this matrix special took me a little bit to actually come up with it, right? Because normally if you just throw a random matrix up here, it's going to be full rank because it's hard to sort of get linearly dependent columns. But I did here, and here's the method to my madness. Let's say I take the first column plus 4 times the third column. I'm going to say that equals the second column. You think I'm right? So I'm taking 1, negative 4, 5. I'm taking that triomino, one of those, plus 4 of the 2, 2, 2 guy. And I'm claiming that that gives us one of the 9, 4, 13 guy. And you can work that out and tell me if you think I did my math right. I think I did. And the rank of this thing, the rank of C, ends up being 2. Now, just from this analysis, all we knew is that it wasn't 3. We knew it wasn't full rank, right? Because we found some linear dependence. It's certainly possible to have a matrix that is only rank 1, even though it's 3-dimensional here, right? So let me give an example of that. Let's say we have this matrix here. Let's make it 1, 2, 3, 2, 4, 6, 3, 6, 9. Now, you can probably tell that this guy here is double the first one, and this guy here is triple the first one. And in fact, this guy here is 1.5 times the second one, right? These are all in bed together. These are all the same triomino, and therefore this thing, if we call this D for super deficient, this thing, the rank is 1. Okay? So bottom line is that your average Joe matrix, if you just kind of made a random square matrix, it's going to be full rank. You know, the odds are. Because the only way for it not to be full rank is if you happen to choose some columns where one of them was a linear combination of the other ones, and that in general doesn't happen. It's certainly the case, though, that we're going to turn out to deal with rank-deficient matrices, and in fact, there's a lot of very important operations that depend on matrices being rank-deficient in order to perform their special function. That's coming up soon. One last thing that I'll tell you about is this. The Rank-Nullity Theorem is a thing, okay? Now, what does this mean? First of all, let's talk about what the nullity means. The nullity is the dimension of the null space. Whoa, what does that mean? The dimension of the null space. All right, let's go back to this example we talked about where we had this guy. We had 1, 3, 2, 6. Now, you will remember that this is blue dominoes. You will remember that the rank of this matrix is 1. We'll call this E since it's the 5th one we've looked at this segment. We know that rank E is 1 because there's only one linearly independent vector out of these two, right? So the rank of E is 1. Now, the null space of this thing, remember we said, hey, what is the null space, also known as the kernel? And we said, well, we can think of some vectors that are in that thing. In fact, we thought, what if we have 2 of the first column and -1 of the second column? That was one. We said, well, what if we have 4 of the first column and -2 of the second column? That's another one. What if we have 8 of the first column and -4 of the second column? Well, that's going to be the 0 vector. What if we have -3 of the first column and 1.5 of the second column? Now, you may be wondering where I'm getting these, and it's because I've already seen the pattern here. But basically what we're doing here is we're saying that twice the first minus the second gives you the 0 vector. Therefore, look at this. If I take that guy right there and I multiply him by 2, I get that guy right there. And if I multiply him by 4, I get that vector right there. And if I multiply him by -1.5, I get that vector right there. And so basically, the weird way to think about this is that the null space vectors themselves are all on top of each other. 2, -1 is right there. 4, -2 is right there. 8, -4 is right there, barely on the screen. -3, 1.5 is right there. Look at this. These are all on a line. I can't draw a straight line, but that's bad. Sorry. Those are all on a straight line there. And it sort of has to be that way because we've only found kind of one way to exploit this, right? We've found that, this guy here is a multiple of this guy here and vice versa. Therefore, if I have this special ratio, right, if I have a certain number of the first guy and negative half that many of the second guy, I'm going to get the zero vector if I add them up together. And so the nullity of this matrix is 1. The nullity of E, and sometimes they'll say null E, or sometimes they'll say nullity of E. I've seen both notations. For this particular thing is 1. Okay? Now, that is the dimension. That's what we mean by the dimension of the null space, because you see the null space here is only one-dimensional. It is a line. Now, here's the Rank-Nullity Theorem, which actually, once you get it, you're like, yeah, that makes total sense, but at first it seems like a mind-blower, and that's this. For any square matrix I give you, the rank plus the nullity is the size of the matrix. If I give you a 2 by 2 matrix, the rank plus the nullity is going to be 2. So if I give you 2 yellow dominoes, if I give you a perfectly regular, happy 2 by 2 matrix, it's going to be full rank, the rank is 2, and the nullity is going to be 0, because the only thing in the null space is the 0 vector itself, and just the 0 vector has dimension 0. If I give you that E matrix that we had just now, the green one down here, right? This thing has rank of 1 and nullity of 1, and sure enough, 1 plus 1 equals 2. If we look at this matrix we had before, where we said, hey, what about 1, 9, 2, negative 4, 4, 2, 5, 13, 2. Remember, we looked at this and we said this thing has rank 2. I forget what we call this. I'll call it F because we're moving on. Rank F equals 2, right? So if I asked you, what is the dimension of the kernel here? What is the dimension of the null space? You could tell me that it's 1. And the reason you know that is because the Rank-Nullity Theorem says the rank of any matrix Q plus the nullity of that matrix is going to be equal to the size of the matrix, or some people call it the dimension of the matrix, right? So I've got 3 different columns here. If they're all independent of each other, I'm going to get full rank and I'm going to get no nullity. If 2 of these are dependent on the third, if I've got 1 of these that you can make out of the other 2, then it's going to have 1 less than full rank, and the nullity is going to be 1. If I've got that matrix we did where we said 1, 2, 3, 4, 5, or no, I'm sorry, 1, 2, 3, 4, 6, scratch that. 1, 2, 3, 2, 4, 6, 3, 6, 9 is what I meant to say. Sorry about that. This matrix here, I'm going to call it G. Remember, this thing had only 1 rank, so I can tell you right now that its nullity is going to be 2, which means this thing is so bogus, it's so screwed up, all 3 of its columns can be gotten from any of the other ones, that its null space is actually 2-dimensional, and that means there's 2 degrees of freedom in terms of how I choose the different columns to add up. It's a little bit abstract to think about, but the only thing you have to understand now is that the lower the rank of a matrix is, the more different ways there are to exploit it by being able to get the 0 vector in more different ways. And that's really all you have to understand about the Rank-Nullity Theorem for this course.